Today we are going to discuss the design numerical of Battened compression member. A column 4 meter long has to support a factored load of 600 kilonewton due to dead load and imposed load. So this factored axial compressive load of 600 kilonewton is because of dead load and the live load from the structure. The column is effectively held at both the ends and restrained in rotation at one of the ends. So if you write the given data, this is a column and the end conditions are given. The column is effectively held at both ends. So at both ends, it is effectively held. That means the translation is restrained at both the ends. So this end is not allowed to move in either direction and restrained in rotation at one of the ends. So one end is restrained against rotation. That means this end, it is restrained both in translation and rotation as well. But at one end, at other end, only translation is restrained. Now this end is freely allowed to rotate. So this is the factored load, and if you apply factored load, this column buckles like this. Now this end, the rotation happens at this end. So this end is not restrained against rotation. It is only restrained against translation. That is the end condition. So one end is pinned, other end is fixed. For fixed and pinned end condition, if you refer IS 800-2007, table number 11, for fixed and pinned condition, you can refer this. First indicates at one end and the second indicates the condition at the other end. And here, this is the translation, restrained, this is rotation, also restrained, that is fixed end. And at other end, translation is restrained and rotation is free, that is pinned end. So fixed and pinned. For fixed and pinned end, effective length is 0.8 times the total length. So effective length of the given column is 0.8 times the total length. So total length is 4000 mm. So effective length is 3200 mm. What else is given? Apart from the end condition and the total length, we have factored load. So factored load, factored axial compressive load. Is 600 kilonewton. So for this 600 kilonewton, we need to design a battened compression member. Okay, see, before solving this numerical, we'll discuss about the procedure. First, what we need to do is we have to design the compression member. Design of compression member. So since we are going to design a battened column, we are going to select two channel arranged back to back at a spacing of S. So this is how we have to design a compression member. In designing a compression member, first step is we need to assume design compressive stress FCD. Then you have to determine the area required to withstand the applied factor load. Once you know the area required, now you have to select a section from steel table or any other relevant code. Once you have selected the section, then you have to arrange it in such a way that Iyy should be greater than or equal to Ixx. Minimum moment of inertia has to be greater than or equal to maximum moment of inertia. Once you have arranged it, that's it. That is the compression member. You have selected a compression member, but you have not checked whether this selected compression member can withstand the applied factor load. So in the end, you need to check the strength of compression member. For checking its strength, we have to calculate the load carrying capacity of compression member, which is equal to area into design compressive stress. This design compressive stress should be calculated for the section we have selected from the steel tables. For that particular section and its arrangement, how much is the design compressive stress it can take, and the area of member. If you multiply both, you will get to know the strength of the chosen compression member. If this strength is greater than or equal to applied factor load, then your compression member is safe to withstand this load. Okay, we have designed a compression member. Is that all? No, because we have selected two channel section and we have placed at a distance s away from each other. So in that situation, if this two channel has to act as a single compression member, then you have to connect it. You have to connect both this channel such a way that it acts as a single column. So we are gonna connect using a batten. So that means you need to design a batten as well. Design of batten. So how we do it? First, we'll find the size of batten. Here size in a sense the depth and the thickness. Once you know the depth and thickness, next we'll calculate the length of batten. Once you know the length, next we'll calculate the spacing of batten. Now at what spacing we need to provide the batten. Once you know the size, length and spacing of batten, you have to determine the force on batten. Batten is subjected to shear force and bending moment. So you need to know how much is the shear force and how much is the bending moment. And in the end, you need to check the shear strength and bending strength. If this shear strength and bending strength is greater than the shear force and bending moment, then your batten is safe. Once you have designed the batten, what else? Is that all? No. Still, small step is remaining, because we have designed a compression member, we have designed the batten, but we have not designed how we connect this batten with the compression member. So the last one is design of connections, or design of connection of batten with the compression member. When you are designing a connection, either you can design a bolted connection or welded connection. This is the design procedure of a battened compression member. Let's solve this numerical step by step. First, we need to design a compression member. In that, you have to assume the design compressive stress We'll assume that as a 160 Newton upon mm square. Next, you need to calculate how much is the area required to withstand the applied factor load. So area required equal to factor load upon assumed design compressive stress. Factor load is 6,600 kilonewton. So I have converted it into Newton by multiplying 1000 upon 160 Newton on mm square. So the area required is 3750 mm square. So if I convert it into centimeter, 37.5 centimeter square. Since we are going to select a two channel section, so I need to know how much is the area required for single channel. Which is equal to 37.5 upon 2. That is 18.75 centimeter square. So now I need to select a section from steel table. So how I have to select a section? I have to select a section in such a way that its area is equal to or greater than area required. So I am going to select ISMC 150 at the rate of 16.4 kg upon meter. So from steel table, I am going to select ISMC 150 whose area is 20.88 centimeter square, which is more than 18.75, and the other properties are given here: depth of section, width of flange, thickness of web, then CG, moment of inertia in XX and in YY, then radius of gyration in XX and radius of gyration in YY. So let me note down all the property. This is the channel, which is ISMC 150 at the rate of 16.4 kg per meter, whose depth H is 150 mm and area of the section is 20.88 centimeter square. If I want to write it in mm square, then it is 2088 mm square. Thickness of flange is 9 mm. Thickness of web is 5.4 mm. Then CG is at a distance of 2.21 centimeter, 2.22 centimeter. That means CY equal to 22.2 mm. Then moment of inertia about XX axis. Let me write this as a small x because this is single channels moment of inertia. Small XX and small YY. So small XX is 779.4 centimeter per 4. And radius of gyration about small XX axis is 6.11 centimeter. Moment of inertia about the minor axis small YY is 102.3 centimeter per 4, and radius of gyration about the minor axis small YY is 2.21 centimeter. Okay, these are all the data which is required for our numerical, so I took it from steel tables. Once you have selected the channel section, next step is you need to arrange it in such a way that the moment of inertia about the minor axis to be more than or equal to moment of inertia about major axis. This is two channel section. I'm going to arrange back to back, and this is the global axis XX, and this is the global axis YY. As we know, the individual moment of inertia of the channel section lies here. Major axis XX and minor axis YY. So we need to arrange in such a way that this YY moment of inertia has to be greater than or equal to XX moment of inertia. Moment of inertia, global moment of inertia about axis YY should be greater than or equal to global moment of inertia about axis XX. So if you expand this, YY IG plus AHY square. See, we have discussed about this even in the design of lacing or laced column member as well. So please refer that for the detailed information about this moment of inertia and the arrangement. As we have discussed already, Hx is 0, so this term is 0, so you will get only this term in here. So Iyy is 102.3 into 10 to the power 4 because I have converted it into mm power 4 plus area of single channel is 2088 in mm square plus Hy is the distance between local axis to the global axis. So this is the Hy. So what is Hy? If this is the spacing, we are going to arrange. This distance is half of that spacing and this distance is the CG distance from this corner, CY. So Hy is CY plus S upon 2. So here S upon 2 plus CY is 22.2 mm whole square. So this whole term should be greater than or equal to Ixx. That is 779.4 into 10 to the power 4 mm power 4. Okay, if I solve, I will get how much is the spacing. Spacing should be provided greater than or equal to 69.49 mm. So if I provide a spacing of 70 mm, that means spacing greater than the required. That means this term, the left hand side will be greater than right hand side, or in a sense this will be greater than this. So in the end, the minor moment of inertia is moment of inertia about the global Ixx. That is my minor moment of inertia, and the corresponding radius of gyration, I have to use that in this numerical. So that means minimum moment of inertia, minimum moment of inertia is Ixx. That is 2 times, because we have 2 channel. For one channel section, which is 779.4 into 10 to the power 4. If you refer here, this is the minor moment of inertia. Hx is 0, the whole term is 0, so it is twice Ixx or Ig. And my minimum radius of gyration is Rxx, which is exactly equal to R small xx. Please refer the previous design numerical on laced compression member. We have discussed about how the global radius of gyration about xx and the local radius of gyration of one channel R small xx will be equal. We have discussed about this, okay? So which is 61.1 mm. Okay, this is the minimum radius of gyration and minimum moment of inertia. Okay, once you have arranged the compression member, you need to check for its strength. That is the last step in the design of compression member. Check for its strength. So strength of this chosen compression member PD, which is equal to area of the compression member into its design compressive stress. We know how much is the area because we have 2 channel section. One channel section area is 2088 mm square. So we need to know how much is the design compressive stress FCD. Once you know it, if you multiply with area, you will get the strength. If this strength is greater than or equal to factor load, then your column is safe. Now let's calculate the FCD for the chosen section. So for calculating FCD, you need to know its buckling class. What is the buckling class for built-up section? If you refer IS 800 2007, in page number 44, table number 10, we have for built-up section. For built-up section, the buckling class is C. So buckling class is C. That means you need to refer table 9C to determine the design compressive stress. Okay, if you want to refer table 9C, there are two parameters you need to know. One is the yield stress of the material. Since we are using mild steel, yield stress of the material is 250 Newton upon mm square. The second one is slenderness ratio. So you need to calculate how much is the slenderness ratio. Slenderness ratio is effective length upon least radius of gyration. We know the effective length is 3200 mm and the least radius of gyration is 61.1 mm. The slenderness ratio is 52.37. Whenever we calculate slenderness ratio of a compression member, you need to check with the maximum permissible slenderness ratio, which is also given in IS 800 2007. For a compression member subjected to dead load and imposed load, the maximum slenderness ratio allowed is 180. Since the slenderness ratio is less than or equal to 180, the chosen compression member is safe in buckling. Otherwise, you need to revise it. Okay, once we know the slenderness ratio, you need to refer IS 800 2007 table 9C. This is table 9C. So in table 9C, yield stress of our material is 250. So for 250 and for the slenderness ratio of 50, the design compressive stress is 183. And for slenderness ratio of 60, the design compressive stress is 168. So let me note down this value in here. For slenderness value of 50, the design compressive stress is 183. For slenderness value of 60, the design compressive stress is 168. So for this slenderness ratio of 52.37, the design compressive stress will be calculated. So I am gonna do the linear interpolation. That also we have already discussed in all the design numericals on compression member. Please refer the corresponding video for that. And the design compressive stress corresponding to 52.37 slenderness ratio is 179.445 Newton upon mm square. See, once you know the design compressive stress, the design axial load carrying capacity is area into compressive stress. So 2 times 2088 into 179.445, which is equal to 749.36 kilonewton. That is well above the factor load of 600 kilonewton. So the chosen compression member is safe to transfer the axial factor load of 600 kilonewton. It is safe. Okay, now we have designed a compression member. And now we need to design the batten. This is the plan of our compression member. We have two channels connected back to back, spacing of S, and it is connected by Battened on both front and back. So this is the front view. This is the top of the column, and in the top we are going to provide end batten, and in the middle we are going to provide intermediate batten. So this is intermediate batten, and this is the end batten. And we are going to arrange this channel at a spacing of 70 mm. And this channel we have selected is ASMC 150 at the rate of 16.4 kg upon meter. Now let me draw the global axis alone, XX, and this is the YY. Okay, see, in designing a batten, first we have to find the size, length and spacing of batten. So first design of battens. So in that you need to determine the length of batten. Okay, what is the length of batten? And we know this distance is 70 mm, and we are going to connect using bolts, and we are going to provide first bolt no matter whatever the number of bolt you provide. So we are going to provide first bolt at a gauge distance of 30 mm. So that means the length here is 30 and here is 30. So the length of batten, which is equal to 30 plus 70 plus 30, which is 130 mm. Now we need to determine the thickness of batten. So thickness of batten T equal to length upon 50, which is 130 upon 50, that is equal to 2.6. So we'll provide 3 mm thick. So minimum thickness should be 2.6. So we are going to provide 3 mm. Okay, once you know the length and thickness, now you need to calculate the depth of batten. As I said, here we have two batten. One is end batten and all the other remaining battens are intermediate batten. So you need to find depth for both the battens. For end batten, the effective depth should be greater than or equal to 2 times the width of flange, or A. Now what is A? If this is the channel we have connected back to back, A is the CG of one channel to the CG of other channel. That is the A. Now what is the CG from the corner, which is 22.2 mm, and on this side the CG also is 22.2 mm, and at what distance we have placed two channel back to back, which is 70. So A equal to twice 22.2 plus 70, that is 114.4 mm. Now what is the width of one flange? Width of one flange is 75 mm. That is the width of flange. So the depth of end batten should be greater than or equal to twice the width of flange, 75, or 114.4 mm. Whichever is maximum, that is the minimum depth we need to adapt. So here we will get 150. So this is the maximum value among these two. So that value we need to adapt as a effective depth of end pattern, which is 150. Okay, now what is overall depth? See here, if you go back to this, see we can even arrange the bolts like this. So from this center to this center is the effective depth. The overall depth is this, is the overall depth of end pattern. So overall depth is effective depth plus here this end distance. You need to add end distance on both the sides. That is the overall depth of end pattern. So overall depth of end pattern, which is equal to, I'm going to provide 30 mm as end distance plus the effective depth plus 30 mm the end distance on the other side. So which is 210 mm. That is the overall depth of end pattern. And for intermediate pattern, the effective depth is greater than or equal to 2 times the width of flange or 3/4 A. So again, this is the maximum value 150 mm. Already A is less than 2 times the width of flange. In that, 3/4 of A will be much lesser than this 2 times the width of flange. So this is the maximum value. So we'll adapt effective depth of intermediate pattern also as 150 mm. Overall depth of intermediate pattern, which is also equal to 150 plus 2 times the end distance, so which is 210 mm. Now we need to determine the spacing of this adjacent pattern, spacing C. So spacing should be provided such a way that slenderness ratio of the single compression member should be less than or equal to 50 and also should be less than or equal to 0.7 times the slenderness ratio of whole column. So we have already calculated slenderness ratio for the whole column is 52.37. So this slenderness ratio of single compression member between two batten supports. Now what is slenderness ratio? Slenderness ratio is effective length upon R minimum. So what is R minimum of one channel? So which is R small yy, that is 22.1 mm. Now what is effective length of this single channel section between two support? Effective length is C. So C upon 22.1 should be less than or equal to 50 and also it should be less than or equal to 0.7 times 52.37. Now if you calculate, C should be less than or equal to 1105 mm or C should be less than or equal to 810 mm. So now let's adapt the spacing of pattern as 500 mm. So it should be less than this value. So I have adapted C as a 500 mm. Now I know all the properties of my pattern. Now I need to determine how much is the force coming to the batten. That means both shear and bending moment. So force on batten. Transfer shear is Vt, which is 2.5% of column load. So Vt is equal to 2.5% into column load is 600 kN. So transfer shear is 15 kilonewton. So what is my longitudinal shear then? VB. So longitudinal shear VB equal to BT C upon N. Now S is the transverse distance between the bolt groups of one channel to the bolt or weld groups of other channel. See, that is this length of batten. So 30, 70, 30, 130. That is the length of batten. So Vt is 15 kilonewton. So I'll substitute in kilonewton itself. Let me convert it into Newton. And C is the spacing of batten. I'm going to provide 500 mm. So N is always 2 number of battens front and back. And S is the length of batten, which is 130 mm. So the longitudinal shear coming to my batten is 28.84 kilonewton. So I need to check for this shear. If my batten shear strength is more than this, then my batten is safe in shear. Likewise, the moment coming to the batten, M is equal to BTC by 2N. So Vt is 15 kilonewton. So let me multiply with 1000, and C is again 500 divided by 2 times N is always to front and back. So the moment I am getting is 1.875 into 10 to the power 6 kilonewton meter. Okay, now I know how much is the force on batten. Now I need to check its strength of batten. Now let me calculate the shear stress in batten. Now due to the longitudinal shear BB, shear stress is shear force upon the cross sectional area. So shear force is 28.84 into 1000 Newton upon depth of my batten is 210 into thickness of my batten is 3. This shear stress due to applied shear force is 44.78 Newton upon mm square. We need to check if this shear is less than or equal to permissible shear Fy by root 3 upon gamma m0, then it is safe. Now we need to know this value. So Fy yield stress is 250 and the partial safety factor of material gamma m0 is 1.1. So this value comes out to be 131.21 Newton upon mm square. So since our shear stress on the batten due to applied load is only 44.78, which is well less than maximum permissible. So the chosen batten is safe in shear because shear strength is more, or the shear stress due to applied load is less than the maximum permissible shear stress. So next I need to check the bending stress in batten. So bending stress Fd equal to m by I into y. This bending stress due to applied moment, if it is less than or equal to the maximum permissible bending stress gamma Fy by gamma m0, then it is safe. Let's check it. 1.875 into 10 to the power 6 upon d cube p by 12 into d by 2. So d is the depth of the batten, d is the thickness of the batten. So it is coming out to be 85 Newton upon mm square. That is the bending stress due to applied moment. If it is well below the maximum permissible stress 250 by partial safety factor gamma m naught, this value is 227.27 megapascal. So since the bending stress due to applied load is well below the maximum permissible bending stress, so our batten is safe in bending also. So we have designed the compression member and also we have designed the batten. Now we need to design the connection of batten with the. Okay, here we have designed the compression member and we have designed the batten as well. Now we need to design the connection of batten with the compression member. So design of connection. Okay, now this connection is not as same as axial connection. This is eccentric connection since we have movement in the member. We have shear and also movement in the member. So this is eccentric connection. So the number of bolts required for eccentric connection should be square root of 6m by rpm. Okay, here m is the moment, r is the shear strength of bolt, p is the pitch at which the bolts are arranged, m is the number of chain of fastener. If this is our end connection, so I have drawn a channel, single channel and the pattern with the end. Now if you are going to provide, suppose for example, I don't know how many number of bolts are required, just for explanation I am drawing 2 chain of bolt. If I am going to arrange in 2 chain, then this m I need to substitute as a 2. Now pitch, suppose if the distance between 2 fasteners is the pitch. So it all depends on what size of bolt I am going to provide. So let me assume the dia of bolt. So assume I am using, let's say, 16 mm dia bolt of grade 4.6. That means my minimum pitch to be provided is 2.5 times B16. So what is the minimum pitch I have to provide is 40 mm. So that is the minimum pitch I need to provide. I can provide even more than 40 mm. And now I need to calculate, suppose if I am providing 40 mm as the pitch. Now how much bolts can be arranged in one chain? So total width of my member is 210 and in that the edge distance is 30. Is 30 mm. So how much is the remaining in between? So if you subtract 210 from 30, it is 150. That is the effective depth of batten. So in this effective depth, if I am going to provide a pitch of 40 mm, how many number of bolts I can provide in a single chain? Suppose if I provide a 3, now what is the distance? 150 upon 2, which is 75. So my pitch is here 75, so I can even provide more than 3. So let me provide 4. So this distance is 150. So if I provide 4, now what is the distance? 1, 2, 3. So if I divide 150 by 3, which is 50 mm. So I can provide only 4 number of bolt in a chain. If I go for 5, then this pitch will become less than 40. So the pitch I have adapted, see minimum I have to go for 40, but what pitch I have adapted is 50 mm. So maximum I can provide 4. So I'm thinking that I'm going to provide 4 in a single chain. Okay. So my pitch adapted is 50 mm. Okay. And my end distance is 30 mm. Okay. This is the spacing in which I'm going to arrange the bolt. So I need to calculate what is the shear strength of my single bolt R. Here, this is the shear strength of single bolt. So which is equal to Fu upon root 3. Please refer design of tension member or the design of connection for this detailed description. So the factor of safety, partial safety factor, gamma and B is 1.25. Fu, yield stress of material is, or yield stress of bolt, Fu is 400 Newton upon mm square. Now, how many number of shear failure plane are there in the bolt? If you look at the cross section, this is where we are going to arrange the bolt. So how many number of interface are there between batten and the flange of the compression member? There is only one interface. So you have only one possibility of shear failure plane. So in that shear failure plane, we'll assume only threaded portion exists. So Nn is 1 and there is no shank portion in the shear failure plane. Ns is 0. So totally you have only one shear failure plane. So in here, if I put Ns 0, this whole term will become 0. So I have only this term. So my Nn is 1 and A and B is 78% of shank area, 156.8 mm square. If I substitute A and B and the Nn, Fu, gamma, Mb, the shear strength of single bolt I am getting is 28.97 kilonewton. So the number of bolts required is, let's substitute all the value in here, square root of 6 into moment upon RPM. So N, which is equal to square root of 6 into moment, which is in Newton mm. So R, I have to substitute in Newton. So 97 into 10⁻³ . So the pitch I am going to adapt is 50 and the number of chain is 1. Let's assume I am going to provide only one chain of bolt. So number of bolt required is 2.78. So I can provide, I am going to provide 3. So I assumed I am going to provide 4. So that is why pitch I am going to adapt is 50 mm. Now I got only 3. So the pitch I am going to adapt is 75 mm. So if I substitute 75 mm, again my number will come down, but it won't go below 3, below 2. So I am going to adapt to 3 and my pitch is 75. So all this detail will be specified in the detailing. So if I substitute my pitch as 75 now, so the number of bolt required I am getting is 2.27. Anyhow, we are going to provide 4. So there is no issues in providing 75 mm as a pitch distance. So all this detail has to be clearly mentioned in the detailing drawing. Thank you very much.